Yep. Okay. Thank you. And I will turn my video on to be friendly. Hi, everyone. So thanks for joining everyone today. So this is the early experiences preparing for Aurora session. And so it'd be myself, Chris Knight, and some colleagues here at Argonne and ALCF, Abhishek Magasetti, Yasmin Godard, Timothy Williams, and Yelo. And then we'll the plans for the session. So I'll start off with a very quick intro, really just sort of set the stage and then provide some reminders to folks who may not be following the Aurora activities as intensely as we are. And say a few words about the system and the testbeds that we have access to, and then lead into a lot of the great work that we'll hear about later today in the talks by everyone. And I will say real quick that this is a public session. And so unfortunately, we can't talk about a lot of the more interesting details, the performance, for example, that folks may be interested in. But still, there's a lot of good experiences and practices that we can talk about. And I'll provide a plug, if you will, for an NDA session that's happening this week, where some more involved discussion is certainly possible if folks are on the appropriate NDA. And so very quickly, the Aurora system, and this is sort of the very high level view. It's an Intel HPA machine. It's currently spec'd at with a peak performance of more than 2 exaflops of precision. If like us, you may care more about sustained performance of the applications. So I think this bodes very well for how promising of a machine this will be. Greater than 10 petabytes of total memory. That's both CPU and the GPU, and that's spread across more than 9,000 nodes. If you're not familiar with the compute node architecture, this is consists of 2 of the Intel Xeons, the Sapphire Rapids, 6 Intel Xe GPUs. This is, people may be more familiar with the PVC name Ponte Vecchio. And in the diagram, you can see part of the illustration is the all-to-all connectivity between the GPUs. That is one of the features of this node architecture. Like some of the other exascale systems, this is the HP Cray Xe platform, and with the Slingshot 11 interconnect. And last but not least, one more interesting aspect of this particular machine is the Deos file system. And so not only with more than 230 petabytes of storage and the capability of more than 25 terabytes of bandwidth, enabled by Deos for the production runs, we'll have additional storage as well for that project data. So again, a very quick high-level overview, but if folks are more interested in the latest and greatest news, the facilities update will cover that tomorrow morning at 9 a.m. Central Time, 10 a.m. Eastern. All of the work that you'll be hearing today, and of course, all of the work that's ongoing in preparation for Aurora, is making use of testbeds. For those that don't have NDA access here at Argonne, one can still make pretty good progress in the public environment. And so that's mainly enabled today with the Intel Dev Cloud, and downloading yourself the public One API SDK toolkits. And so if you have a relatively modern Intel CPU, for example, you may not realize it comes with an integrated GPU. And so that GPU combined with the One API SDK that you can download, it makes for a pretty decent development environment to at least get started and write functional code, for example. Here at Argonne in JLSC, we have a handful of test beds that the teams have been working on over the years. Primarily in the beginning, it was the integrated GPUs that I just mentioned. It was a primary development vehicle to really get everyone started quickly. Then more recently, working with the Articus and very recently the Florencia nodes. And so these are Intel Xe GPUs, and in particular, these Florencia nodes are our PVC GPUs. And more of this will be discussed at the hands-on session later this week on Friday for those that are on the NDA. And if you want, there is some information available on the ECB Confluence. If you navigate to the Aurora application integration space, or if you search in Confluence for Florencia, you can find some details there. In particular, if you don't already have access to the JLCF resources, there's instructions there to get access. And folks, particularly on the ECP side, who have access to the JLSC resources, you may not realize, but you also have access to another cluster, the DevEP cluster. And so that's another set of 32 nodes that are very similar to Articus. And that actually the hardware and the software very much mirror what we have in JLSC. And so that's very much a second resource available to the ECP community, again, on the NDA. From the software perspective, and again, I'm only really focusing on the programming models, and there's not the broader software ecosystem. The Aurora applications are using any of a number of programming models, and I think this is one of the great things about the Aurora and the software environment. And so, OpenCL, it's very likely HIP will be enabled via a separate HIP LZ effort that's funded by ECP. Predominantly OpenMP and DPC++ SYCL, and then also the abstraction layers Cocos and Raja. And so there's been many opportunities and many options for application developers to have chosen, and these were key decisions folks were making years ago as they initiated their preparations for Aurora. And so this is a slide that we who have presented on Aurora topics we've shown this over the years. It's already going on a number of years old, and I think we've left it somewhat static. And so this is a snapshot in time, if you will. And it's kind of interesting to think about how this image would change given the state of applications today and then the maturity of applications that are developing in OpenMP and SYCL, for example. And so years ago, many projects, many of the folks in this session had to make key decisions of how they're going to write their application to target multiple vendor GPUs. And with the case of Aurora, we had laid out this mapping. And so folks who had predominantly had a CUDA application, what were the most likely pathways for them to modify and port their application, possibly likely to a new programming model. I mean, especially in the case of CUDA. But to do that porting and to arrive at a solution that was both portable and performant across the systems. And today, with these early experience stories, we'll hear some about that work and the decisions that went into that planning. Some of the work with taking a Cocos application and the modifications to enable not only the CUDA backend, but to enable multiple GPU backends. To then enable running on, for example, Aurora and Frontier. Some work on how to migrate to DPC++, and some of the gotchas and best practices there that have been developed over the past couple of years. And in particular, in some applications, an interesting thing I think that's emerging is many of these errors are one-to-one that go from one program model to another program model. And today we'll hear about one effort of actually making use of two programming models, OpenMP and SYCL. And so I think this image is nice as a snapshot in time, and I think it's exciting to see where this is going to head if we were to do another image in a couple of years now as we prepare for the machines post Aurora and Frontier. And so with that, we have a set of four presentations that all in the spirit of early experiences and best practices and sharing of knowledge to others that are preparing similar efforts for Aurora and so on. And we'll go in the order on the screen here. And so I would encourage if there are questions throughout, we'll be watching the chat. If the speaker gets to the end of a slide and they finish their thought and you have a question, I think that would be an appropriate time to ask if it's a quick one. I would save the more in-depth conversations maybe till the end of each individual talk. And then at the end, assuming there's time, we can have general Q&A if folks are interested in the topics that have been presented or other early experiences that we can comment on here today. And so with that, I will pass the microphone to our first speaker, Abhishek Bagasetti, who will be talking about his experiences with porting to DPC++. So
thanks, Chris.
Stop sharing.
Okay.
Looks good.
Okay. Thanks. All right. Good afternoon, everyone. I'll be talking today about some of the porting aspects to DPC++ that are not so trivial. So I'll be talking about uh, uh, on topics like device and context in SYCL, shared local memory in SYCL, and what is level 0. So at this point, most of the projects who have adopted SYCL or DPC++ as their programming model must have come from a highly optimized CUDA environment, CUDA legacy software projects. Because as Chris was just saying, that SYCL as one of the programming models supported in Aurora has evolved in time, and it has a resemblance, a one-to-one mapping with CUDA, which makes any developer for ease of porting. So SYCL at this state of things, I'll be jumping into the slide which talks about devices here. So device is nothing but an acceleration offload hardware target. And SYCL has a concept called subdevices, or in other words, in OpenCL, it is also called as subdevices. CUDA, what has recently been called as MIG mode, multi-instance CPU mode. So this is nothing but where you can take a device, partition into several subdevices. So that's what the entire subdevice strategy here is. Usually, the terminology states two things. One is explicit scaling and implicit scaling. And many might have already heard these terminologies before, but I'll just be brief about that. Explicit scaling is nothing but where you take a given GPU, partition it into multiple subdevices. Most cases, it is usually across the NUMAB boundary domain. And these subdevices are further used as pseudo devices. So the natural tendency is one creates a subdevice from a root device, and SYCL queues are created based on these subdevices. And we have heard that this process has generally yielded in better performance. And the second default strategy is implicit scaling, where you just take the root device or the root GPU and just use it as it is, and use that to create a SYCL queue. So I've been using here SYCL queue as a term, which is nothing but a way to submit any task to a GPU in the SYCL programming model. So I have shown here a code snippet. The first block is for explicit scaling. So the line just states that get device is nothing but just give me number of GPUs on a node. So I have passed here explicitly the device type as GPU. So on a given device, it just gives you a vector of GPUs. And this for loop just goes over the vector of these individual GPUs and then creates the subdevices. So you create subdevices, and the queues are created based off of these subdevices. So this is again explicit scaling, very well-known technique. And implicit scaling is nothing but, again, the same strategy. You just query the number of devices, loop over each device, and create a queue associated with each device. So let's say each device has two subdevices. So in the explicit scaling, you get to see two more devices for each device. And that's how things see. And I'll talk about why creating a subdevice and all the business of creating SYCL queues is important in terms of performance. So in the previous slide, I have talked about like SYCL queues and what they do. So SYCL queues, again, provides a mechanism to submit work to a device or a subdevice in the explicit scaling case. The most overlooked concept in SYCL is SYCL context. This has relevance to CUDA context again, and also OpenCL context. So let's say, for an example, we have a code which just creates a queue as shown here. So behind the scenes, the runtime actually creates a context for you. And I'll get into more detail about what is SQL context and why is it so important to consider? So SQL context has predominantly the main purpose of resource isolation and sharing. So what, in other words, it does is this provides the visibility between devices. So can a resource, this resource can be anything. It can be a memory space. It could be any handle. Can this resource handle of SQL is visible to other devices or not? That's what predominantly the context does in this case. So SQL context may consist of one or multiple devices. So you could just create one for each device, or several devices can share the same context. So yeah, again, the third bullet just says here the same thing. So the root device and all of its sub-devices can be within the same context. And the most important thing here is memory created can be shared only if the queues are created using the same context. So so when you allocate a memory using a queue, if the queue has different contexts associated with it. So in this case, you have Q1, if you can see the mouse pointer. So if you create multiple of these queues, each queue implicitly creates a SQL context. So any memory that is allocated using all these multiple queues cannot be shared. That's the side effects of this. So context, in short, creates this either resource allocation, resource isolation, or sharing, and depending upon how you create a context and how you tie that up with the queue. So it would be worth taking a look at all the constructors of queue and see what they do. In this case, it's a default constructor. It implicitly creates a SQL context. There are other constructors which explicitly takes a queue, which explicitly provides provision to supply a context. So that's the business with context. So coming to the queue, these queues are nothing but like CUDA streams, loosely speaking. And queue is always attached to a single device in a possibly a multi-device context. And the main purpose of this queue is anything that you submit to the device or a GPU can be executed asynchronously with respect to the host. That's the first. Second is SQL queue can execute tasks, anything that you enqueue it. It could be a mem copy to and fro from the device, or it could be a kernel that you launch on the device. All these tasks can either run in order, like everything runs serially, one after the other, or out of order, where in case any of these queue or compute operations can run concurrently. It all depends upon the data dependencies. Again, so SQL in-order queue, if a queue is created with an in-order as the property, it mimics CUDA streams, which is by default FIF, first in, first out. So SQL queue in-order would be pretty much the same as a CUDA stream, in other words. So the slide just talks about what is the importance of context, how do they get created, and what is the purpose, and what is a queue? What is the main purpose of it? So talking about programming for multiple tiles on a given device or multiple GPUs on a given node. So there are four strategies here from left to right. So A being the most performant one, and D being the least. And I'll briefly get into like explain about in detail about these four models. The first one here is you have a GPU, a root device, where you and you do an explicit scaling. In this, what I mean by explicit scaling is you create sub devices. In this case, we create 2 tiles, and each tile creates its own queue, and that is shown in the code here. So in the figure here, each queue creates its own context. So everything is isolated here. You cannot do any resource sharing between these 2 tiles. And since most of the resources are tied up to each tile, this provides the best mechanism because there is no bookkeeping being done. And hence, this is the reason why it is considered to be the most performant in most cases. The second here is you don't do explicit scaling. You just do implicit scaling, where you do not create any tiles. You just use the GPU as it is. So so A and B are the two most frequently used approaches for many projects in the ECP space. Coming to the least common options are C and D, where you create multiple tiles. So this is again explicit scaling, but these two tiles shares the same context. If you see the constructor here for the queue, you pass in a context as a parameter, and this context is being shared by all subdevices. So in other words, you create queues explicitly for each tile, where you enqueue all your compute and kernels, sorry, copy and kernels. But both these queues create the same context, which means you can just pass the data between back and forth, share the data between these two tiles. And other extreme cases, you share. So the case C deals here with data sharing between tiles, and the case D talks about data sharing between GPUs on a node, on a multi-GPU. So you have two GPUs, for example, on a node, and you create a shared context that is being shared between multiple GPUs. So A being the most performant and D being the least performant. So projects should go back and mostly look at how they are creating the queues. Is it in order, out of order? Would an explicit scaling make sense for us? Where do we have a need to share the data? So all these questions can be answered if you go back and look at how queues are created. That would unravel all the questions that I've just posed. Moving on, shared local memory. This is one of the optimizations that SYCL provides. This is nothing but like a shared memory from CUDA, which is just local on a CUDA block or a SYCL workgroup. So the most important update here is SYCL shared memory can now directly be allocated inside a device kernel with this API, group local memory. Earlier, until now, majority of the projects would be doing what is shown in the red snippet here. You create a buffer with a local accessor and explicitly pass it as a pointer to a kernel. So all this local memory is created outside the kernel call. So the inconvenience here is you create a local memory outside the kernel and then pass it as an explicit pointer. So this additional argument might be an inconvenience with respect to your design. So if you have CUDA, HIP, and SYCL, and then you're trying to just have a one single function definition, SYCL would in fact add an additional parameter that would cause an inconvenience of the API design. So with this group local API, one would not need to create any local memory outside of function. So you can directly create a local memory, group local memory, exactly at the same place where you have shared attribute in CUDA. So that way you can unify all these kernel calls or the definitions in your projects. So this is one of the good outcomes of SYCL standards that came in, and that has helped quite a few projects in my experience. So I would state here that Hyper is one of the projects that I have worked with, and this group local API, memory API would significantly ease the design because there are like at least more than 24 kernels which use shared memory in CUDA. So with this approach, much of the infrastructure that Hyper is doing for SYCL can be greatly simplified. Coming to the last aspect, I'll be talking about level 0. You might have heard of this term level 0 in quite a few cases. And this slide talks about just a brief overview of it. Level 0 is nothing but a runtime driver for Aurora exascale architecture. And in other words, it provides API. As the definition says, it provides direct to metal interface for GPUs. So It's the most lowest level API, which provides fine-grained control and like more explicit control on all several of these operations: discovery, allocations, peer-to-peer, everything. So this is an API that provides like most low-level and explicit control. Majority of our users don't use it explicitly, but again, if I had to do an analogy, this is nothing but like a CUDA driver API, loosely speaking. So where does it sit in the hierarchy? You have one API product, so you have DPC++ programming model and several of these libraries, one MKL, one CCL, and all that on the top level. And you have the architecture, the actual hardware at the most bottom level. So whatever is in between, the wafer in between is the low level, the level 0 interface. So this is the driver API that interacts between the high level programming model and the libraries with the hardware. And I found this a neat figure from one of the publications very recently, which talks about like low level programming model and level 0 is listed here. And it just says that, okay, programmability is quite hard if you talk about low level, but the performance would be quite good in the inverse. So I found that quite interesting, and it has been noted in the literature. Talking about how level 0 API can be even used. So I'll be talking mostly about SYCL interoperability, and Yelo, who will be talking in the next few sessions, is about how SYCL and OpenMP can be used in an interoperable way. So I'll be showing a quick snippet of how level 0 can be used inside SYCL and how we solve one of the problems for SuperLU project. The question here is, how do we get free device memory in bytes? So in CUDA, we have an API called CUDA get mem info, right? And that equivalent or similar in functionality doesn't exist for SYCL. So, but we have cooked up a very similar API that can give the free memory and the total memory at a given instance using level 0 interface. So this snippet shows here how we could use level 0 calls inside a standard SYCL. So you could just take this function, put it anywhere in your SYCL core or C++, and there are just 3 headers here in addition to the standard SYCL.hpp header. So you would need just 3 headers for any level 0 calls, use any level 0 inside the SYCL API, and that's it. So we've solved this free memory device memory problem using level 0 in SuperLU. And there are quite a few proposals that are gaining traction to add free memory inside SYCL specifications. So one of the snippets would more easily look like this instead of directly using the cumbersome level 0 API. So yeah, this is one of the code snippets how you could use SYCL and level 0, and if you take a peek at each detail, level 0 is not that hard to even program as well. And one more, just this is my last slide, and this is one more example of how do you do peer-to-peer. Again, in CUDA, you have an API called CUDA device can peer access. So it just says whether I can access peer or not. And such a peer-to-peer access information is not directly available in SYCL specification. And again, level 0 has a very similar API that solves the problem. So this API can be embedded. Again, you have like few headers, a couple of headers, level 0 that belongs to level 0. Include that in SYCL, and that just solves the problem here. So we were able to solve peer-to-peer access problem in Uvinta, one of the Aurora ESP projects, by just using SYCL and level 0 interoperability case. Just to summarize, finally, explicit scaling has shown to show a better performance than implicit scaling in several applications. SYCL contexts are quite important, which is and is often an overlooked topic. and how the sickle queues are created. Now there is a new paradigm for the shared local memory, which can allocate the shared local memory inside directly the device kernel, and how the interoperability works with level 0. And these are just upcoming events that are related to sickle. The next week is SickleCon. There are quite a couple of posters and presentations, and Sickle Community BOF Days would have there are several talks related to sickle, how they are being used in the SD and the AD space, and I've just listed just a couple of them here. Feel free to check them out. That's all.
All right, thanks, Abhishek. Are there any questions for Abhishek? I'm not hearing any. I do think it's great that even from your slides, Abhishek, that a lot of the work digging into sickle and how to actually make use of it in applications has led to improvements in the spec and the standard.
Yeah, that's right. Because whatever the standard is, the standard approach was CUDA could do certain things and sickle cannot do certain things. So it is quite an inconvenience, even someone for porting efforts, right? So we just bring that to sickle specifications, and they just ponder upon that, ratify it. So quite a few of them went into sickle specifications and things to improve. So yes, yeah. The application has driven, in fact, the specs in this case.
That's the great thing about co-design.
I agree.
All right.
Sorry, Aditya from Karlsruhe. I had a question about the shared local memory. I hope you can hear me well. So you said it can be allocated within the kernel now, but do we also need to give the parallel for some information about how much shared memory we'll need?
So yeah, at this point there is. So you're talking about static versus dynamic, and
if it's dynamic, that is, yeah.
Okay, so currently it is just static. So the how much should be known at the compile time, and if you see here, I just had an int, right? I'm just allocating one integer. So if you just want to have like 32, an array of 32 integers, what you can just do is this inside a parallel for. So that's pretty much, you don't need to pass anything from outside, if that answers your question.
Yeah, okay, thank you.
Any other questions before moving on? All right, if not, thanks, Abhishek. It was a great talk. And so next in the list was Yasmin Gadar, and she'll be telling us a short story about her experience with working with the XALT team and getting lamps ready for Aurora.
Can you, okay.
Yeah,
Can you see the slides?
Yes.
Okay, awesome. Okay. Hi, everyone. So I'm going to take a little bit different approach than Abhishek in talking about my experience with porting XALT applications to Aurora. So this is more of a journey of like how we started and then we are today. So XALT, okay. So XALT is basically one of the ECP projects that is looking to extend the accuracy, length, and time scales of material science simulations. They are using their main application is LAMS. Which is basically larger scale MD simulations. And the potential that they are focused at is called a SNAP, which is spectral neighbor analysis potential. And it has multiple different programming models as well as different packages. But my focus today in this talk is going to be mainly on LAMS. So LAMS by itself is written in C++. It does have different backends, GPU-enabled COCOS, CUDA, OpenCL, ROCm. It also has OpenMP target. And the performance of the XALT LAMS project is basically mainly depend on the single node performance of the SNAP. So early on at the beginning of this project, we basically started with the mini app rather than the full application. So the mini app is called TestSnap, which is a standalone proxy app that you can run independently of LAMS, but it does capture all the main kernels that we care about. The test snap by itself actually has different programming models or with Coco's different backends. So that's a great place to start with. So just to give you an idea, it has basically, it goes over to the atom list and a neighbor list and creates a different, so you need to calculate basically energy and forces, and you store them in the 1D arrays. So for the case of Exalt project, they have different, let's say, table of coefficients, and the one that represents the actual problem is the 2J14, which has 15 coefficients. And that's the one I will be showing results throughout this presentation. So the test system is basically made of multiple kernels that they basically calculate energies, they calculate forces, and or derivatives of energies, and they basically store them in a different list. So the main things that you want to think about is compute U, compute Y, compute D, and compute DU. That's the one you're going to see throughout this presentation. So we started with the pure OpenMP offload target because that was what it was available and that was mature enough for us to start testing with. And what we did, we basically identified bottleneck kernels on Intel and NVIDIA GPUs and also AMD GPUs. The profilers was one of the very important tools throughout this process that helps us identify the problems, identify the places for improvement. And every time we made improvement, we pushed back the code to the main stream, the test snap or labs. And this was like sort of the practice. We've been doing that for a while, and I think it's been very helpful. So starting with the OpenMP, we made multiple changes and improved the performance, which I will show in a second. And then those were basis of the starting point when the Cocos becomes mature enough and available on multiple architectures that we can actually start working with that. So the Node Cocos is the one that the Exalt people are mainly focusing on, and that's what basically our goal is. So one of the things we actually learned was during this process was like, there was like a differences within the different backend, which could cause problems in the performance portability, and that's another thing that we have to address. So this was the paper that we published in 2020, which was solely focused on the pure OpenMP implementation of TestSnap. And I've been showing different results throughout this presentation, but the size of the problem stays consistent throughout the system. So that's, if you see different things, that is still for the same system. We have 2000 atoms, the 2J14 with the coefficient number of 15. So, okay, so what are they mean? So basically the blue line was the baseline, the starting point of our study. And then with the red line, what happened, we just basically changed the loop over atom list and a neighbor list using Collapse and OpenMP, which, as you can see, it resulted in performance gain. Different architecture had different performance gain, but all of them did result in that. The green color represents the column major data access pattern, which there didn't really result in performance gain. It was more like a performance regression. So with tuning it more and looking at it, what we did, we changed the loop over there and swapped the neighbor list and the atom list. And that actually resulted in the most performance gain. So we took that final code and then ran it again, kind of looking at the kernels and see which kernels actually is taking the most of the time. And looking at these kernels, you can see the compute Y was the most expensive time. It was different in terms of time on like different architecture, but across all of them, we see this is the one that we need to pay attention. And I want to mention that this is actually very important because it kind of makes us to focus on one thing at a time and know whatever improvement we're applying, we actually have an impact on all different architectures, which helps with the performance portability. So here I'm showing a roofline analysis of different architectures of these kernels. Now in these plots, I do have for different sizes, but I would like you to only focus on the one that is relative to the Exalt problem, which is 2J14, and that represents with the different shapes, but it's all like a full color shape. So that's the one you want to pay attention to. And if you think about the different locations within the roofline, we have the compute bind here, and then we have the memory bind in this side. So you can see from Gen 9 to V100, the system size and everything is the same. You can see the location of the kernels are in the memory bound location. And then if we move into the MI60, this is the same kind of observance, which is still good. So they're all in the same site. So that's, you can still focus on one thing at a time. Well, ideally, we would want them, the kernels, to be compute bound. So that's something that we started looking at and to kind of see what we can do to improve it. Now, here we were working on pure OpenMP offload. At this time, it was like 2021. Now we will have access to the mature enough Cocos that we could actually start working with that. And that's what we did. So the Exalt team and LAMS team actually did a majority of work. This is like a one plot of their work starting from, and you can see there are different versions of the test snap that it was implemented in Cocos. But this V4 that I have the flash upon it is basically, it's like this was the beginning of their porting, which was from the OpenMP version. So they took that, implemented it, and started tuning it. One of the main things they did, they basically used Cocos View and optimized it for share memory. One of the other things that was achieved during this process was like there was a fuse kernel that called compute fuse DEI DRJ, which is you will see in future slides, but that was like through the process of optimization. Now Cocos it does have multiple different backends, the CUDA, OpenMP offload target, SQL, and HIP. And as it's important to pay attention that some of these backends are not as mature as the other ones. So you may be able to run with one backend more efficiently than the other one. And it's important to constantly try them on the different systems as they become available and see with the new test, with the new SDK, with the new architecture, what is the results, and if there is an issue, report it so you can get results quickly. So here, this plot shows the work that I did through on different, with the test snap, with the Cocos basically programming model using different backends and different architectures. So for Intel Gen 9, I used Cocos with the SQL backend. For NVIDIA was Cocos with the CUDA backend, and for AMD was Cocos with the HIP backend. If you look at the kernels, you can see again the compute YI is still the most expensive kernel. So this is the one we need to pay attention to. And in the second graph, I'm basically showing the arithmetic intensity and flops, so you can kind of see what's going on. You can see for the Intel Gen 9, the fuse DEI, DRJ, and the UI are memory bound, but YI is a compute bound. However, in NVIDIA and AMD, everything is compute bound. So that's kind of something we have to look at a little bit further. So we went and did a roofline analysis. So from the beginning of the work to today to the SQL, focus with the SQL backend, you can see sort of there is a shift of, they're still in the memory bound location, but there is a shift of kernels, especially the YI, the green triangular here, and the red circle here. So there's a shift of these specific kernels when we went through the different programming models. And then here I'm just showing comparison between Gen 1, Gen 9, and MI 100, and then Gen 9 with the A100. So you can see there are actually kernels, the locations of them within the roofline is changing. So that kind of prompted us to look further and see what is happening here. And when I went look at the code, I actually noticed that what is happening, that there is a different code path. This is after we actually went through it, but there was a different code path for the CUDA version versus for the SQL version, and also completely different for the OpenMP target version. This is actually something that we will discuss further in our session on ECP app integration tomorrow. So if you want to learn more about what happened with the OpenMP backend of the Cocos, I encourage you to attend that. So that was like something very important because we want a performance portability, and having different code paths may not be the best way to go about it. And the only way we could understand it was using the different performance tools. And for example, in the case of JLSC, we have iProf, which is very lightweight, and you can quickly see which kernels is taking the most time and where it's happening. So that's basically what was going on there, which is something we're still working on it. But everything from the Cocos version was pushed back again to the main branch as well as LAMS. So up until October 2021, we were focusing on a test snap. We were trying to run LAMS but there was like lots of different issues that we couldn't run now. But at that time, we had the Aurora Cocos Hackathon, which was extremely well utilized, and we were able to compile and run the full LAMPS application correctly and on Intel's recent GPUs, which is a great, I would say, achievement, because there was a lot of, and this wasn't done by basically a lot of open communication with Exalt team, with the Cocos developers, with the Intel Center of Excellence people, and a lot of people, as I mentioned here, the Exalt PI, Raul Galatri, and Stan Morag, one of the developers of the Exalt, and also LAMPS, Intel persons, Patrick, Daniel, Chris, and a lot more people. And I think that's very important when it comes to developing and porting in an application to a new architectures, that you constantly in talk with people that are developing different aspects of it. Like, for example, for Cocos, there's a lot of times there's a specific patch that I needed. I would work with the Daniel, I would get it, and I would run it. I would communicate with Dan, with the Stan and Raul to kind of get going and just keep pushing the work. So today, we're actually very happy to say that we have been focusing on the performance of LAMPS on the Intel GPU. It has been running correctly, and we are doing more studies in terms of performance, scaling. This plot that was done by Stanmore is actually showing the kind of throughout the years, how is the performance of LAMPS on the NVIDIA and MI and the AMD hardware has been kind of grown, and like they're basically past their KPP already. But you can see like how increased the performance has been. I am not showing anything related to Intel, but it is running. And again, there's like multiple different backends of LAMPS that we are working on. There is a SYCL, Cocos with a SYCL, Cocos with the OpenMP target, and then CUDA that we're kind of working on and just pushing them, trying them on. It depends on the compiler can have effects. Sometimes there's a regression. You have to kind of pay attention to that and make sure that you notify the compilers developers so they fix the problem. And then the OpenMP target version of it was one of the ones that we're currently working on to resolve some of the issues we have. And the second one is the one that we are mainly focusing as in terms of performance. So basically, we started with the mini app. We use performance tools to identify the bottlenecks. Luckily, the bottlenecks were the same on a different architecture, so we could spend our time to tuning the performance of each kernel, and then we push them back to the main branch. The work we done on the OpenMP was used as a basis for the Cocos development, so we didn't really lose anything. But if we had some availability of the architectures and the maturity of the programming models, we could probably start from the Cocos at the beginning. These changes again are pushed to the mainstream LAMPS. If you want to, you can actually go grab it and do some testing on it yourself. And then currently the focus is on the performance of the Cocos with the SYCL and resolving some issues that we have with the Cocos OpenMP target offload backend. So in general, basically constantly running the code with the new hardware and software, reporting the issues, communicating with the developers and the point of contacts in a teamwork is like what basically enable an application to port successfully on a new hardware and software. With that, I want to thank everyone, and I'm happy to answer any questions you have.
Thanks, Rosie. Are there any questions?
I have a question about the performance on the A100 and the MI250. And if there are two, you showed.
You mean here?
Oh, sorry, not. I think near the end of your slides.
Here.
But not this one.
The plot is a function of PR. The one that Stan made.
Oh, that one.
Yeah, just.
Okay, this one.
So, so here for the MI250, so did Stan run on two devices in a die?
I think he's mentioned that he is running on one die.
So if it is running on 2, will it be higher than A100?
So I need to confirm with Sam, but from what I understood,
I think he is on the list. Yeah, he joins the meeting.
is in the meeting.
But I'm not sure if he is.
Yeah. So I'm just trying to say, like, from the plot, I know he's running on like 1 die. So I don't know if you're running on 2, because maybe 2 that might be twice. But I think from what I understood from the plot, it's 1 die, so it makes sense.
I would, if Stan didn't get the data approved and doesn't want to speak to it, then I would leave it for outside discussion.
Okay.
Yes, yes, because I'm not sure if here I can assume that it is a compute bound application for this snap version, or it is a mix of compute bound and memory bound.
So the roofline analysis that I was showing were only for the test snap, which is the mini app. They were not done for the full lamps. This plot is the full lamps application.
Okay. So we can assume that it is a mix of compute bound and memory bound kernels.
I think the snap kernels are not going to significantly change, but since I haven't actually done the roofline analysis for the full lamps application, I can't really comment on that. But that's one of the things we were planning on doing.
Oh, okay. I see. Oh, thanks.
And I'll just jump in real quick. That Jamin Stan did a reply in chat, and he's got a plug for his talk later today. Okay. If no other questions, we'll go ahead and move on to the next talk. And Tim Williams will talk about his experience with preparing XGC for Aurora.
Okay. All right, are you seeing the slide?
Yep, that's good.
Thank you. Good afternoon, everyone. I'm Tim Williams from Argonne, and I'll be telling you a bit about experience with preparing the XGC application for Aurora. My co-author, Aaron Scheinberg, will dive more deeply on some of the implementation and performance topics in a talk in the particle session this afternoon, so you might want to join that if you're interested. XGC is a particle and cell plasma simulation for magnetically confined fusion plasmas, principally tokamaks. If you look at the grid part of the PIC algorithm, the discretization, because the physics allows, the long way around the torus is very coarse, but within one of those cut planes, it's very fine. And it's an unstructured mesh. And part of the reason for that is to model all the way out to a realistic diverter geometry at the edge of the plasma. So XGC's claim to fame is that it can accurately model this plasma out to the edge, beyond the magnetic separatrix and X point. There are a couple of contexts in which XGC has plans for Aurora. One is an early science project. This is ALCF's Apps Readiness Program for Aurora. And the science problem they'll be looking at is modeling an ITER plasma with the presence of tungsten impurity ions. So the diverter in ITER is made of tungsten, and high energy particles and high heat hitting it can knock off tungsten atoms, which can be ionized and mix in with the fusion plasma. So you've got these super heavy tungsten ions intermixing with super light fusion ions, and this will look at how that modifies the plasma dynamics. There is also an ECP project called WDMAP for whole device model. This looks to couple an XGC simulation of the plasma edge with a concurrent simulation of the core done in a more efficient way with different kinetic modeling. One option for that core simulation is GEM, another PIC code, and the other is GENE, which is a direct kinetic solver that discretizes phase space. These are coupled together with EFIS, and XGC uses Adios for its I/O. So part of the ongoing work toward Aurora is looking at testing on the Deos testbed and implementation of Adios on top of the Deos object store that will be the primary I/O system on Aurora. Last year, some of us in the WDMAP project did one of these ECP podcasts you may have heard, and some of the best practices we distilled out of that are relevant here. First off, if you're doing a GPU acceleration for the first time, if you don't have a GPU-enabled code yet, since the exascale systems are all GPUs, you should consider that process generically and do all that work on today's systems where you can get diagnostics and throughput. Next best practice we identified was, identify a portability strategy that can span, all of the systems you are using and anticipate using on the time horizon that you care about. And as part of that, it's suggested to consider some sort of high-level portability layer you can identify. This might be something third-party like Cocos, or your own library like the gTensor library for Gene. And last, I'll echo what Yasi said, that it's important looking towards the next generation systems, like the exascale systems, to work with the developers of that portability layer to avoid integration surprises. At the top level, the parallelism in XGC is pretty conventional. It's MPI. Each of those cut planes around the torus has at least one rank. It can be subdivided into multiple ranks with subdomains like those shown here. The interesting part and the portability question comes mostly in intranode parallelism. So when running on CPU only, or for the parts of XGC that continue to run on the CPU in a GPU accelerated version, that parallelism is a combination of OpenMP threads and SIMD type vectorization. For GPU acceleration, some years back, the XGC project decided to use Cocos as its portability layer. It also uses the Cabana library from the Copa project, so this is built on top of Cocos, but provides class templates and mechanisms that are useful for particle simulations. Historically, the electron push subcomponent of XGC dominated the runtime of the whole application. And so a lot of work went into optimizing that, even pre-GPUs, using things like sorting and tiling and appropriate data structure choices. Some of that translated directly into GPU acceleration, like using some Cabana data structures and making sure that the layout is GPU appropriate for memory coalesced access. But in general, Cocos is providing for XGC the portability across this set of systems that is currently on its radar, including the two exascale systems. Cocos does give you really good implementation portability, source code portability. What you see here is really essentially all of the differences that are specific to platforms within the XGC codebase. And primarily this is the choice of memory space and execution space from Cocos. And just here to give a flavor, you can see that we're using this Cabana structure to store particles. So you have positions, velocities, some weights for the gyrokinetic approach and delta F. And if you look down in the push, the electron push or ion push, you'll find a Cocos parallel 4 in the middle with a functor that has all the details in it. Likewise, the charge accumulation is a scatter add operation. So if you look in there, in the Cocos implementation, you'll find a parallel 4, again with a functor implementation with a bunch of inline C++ code that amounts to, in the order of 100 lines or so, including, at the innermost, for appropriate architectures, Cocos atomic add. So when the decision was made to use Cocos as a portability layer, the GPU implementation of XGC was much different. It was entirely a Fortran code at that point, and so you can imagine that choosing Cocos for that is a challenge. And Aaron did a lot of meticulous work on mapping of Fortran-derived data types into Cocos data structures and other things, so that incrementally XGC could be moved onto Cocos. And sort of more gradually, from that point to today, the decision has evolved to move a lot of XGC from Fortran to C++. And today, all of the node level parallel execution aspects of XGC are in C++ and using Cocos, whereas originally the electron push, which was a big dominant part of it, was written in CUDA Fortran, and the collisions operator was implemented with OpenACC. So another decision was made that this should evolve as the production version of XGC, so that if you look today at production insight and other calculations going on Summit, it's the same code that we're developing for Aurora. So on some time scale that is, practically possible, pull requests are made, and these changes that have been in process over the last few years become part of the production application. And a key metric there is that the performance can't go down. It needs to be as good as or better than prior performance. And starting with the initial move from the CUDA Fortran to Cocos up through a much more rapid transition to C++ and Cocos, that has been maintained. What you see here is a weak scaling plot on Summit, and I'll from last year. I'll call out a couple of aspects of it. First, the weak scaling is not bad. Second, the profile is relatively flat, so the electron push has been highly optimized, and other time-consuming parts have been optimized and implemented with Cocos Cabana. And so, as you all know from this kind of work, what happens then is that other things suddenly show up in your profile that were invisible before. For example, here you can see the ion and electron shift. This is the passing of particles between subdomains as they move around between the MPI ranks that are affixed to those subdomains. So that has become relatively more important in the profile at that point, and also, as Aaron identified, it was not scaling as well, weak scaling as well as the rest of the components. So that was an opportunity for some optimization that Aaron and some of the Cabana people worked on, and I think Aaron will have some more details on that this afternoon. It took the original XGC Fortran particle shift implementation, which had some advantages of doing a whole bunch of MPI pairwise sends to get good bandwidth. With the Cabana implementation that was nicely encapsulated and sort of merged the two together into something which has some of the advantages of both. It does some particle sorting as well, and does efficient copies as necessary out of these obstructive array data structures we're using for the particles. The bottom line here is that this new implementation is both faster and weak scales better than the other two alternatives. And I don't have the same weak scaling plot with the only thing being changed as this, but I hope you'll take my word for it, or Aaron's word, that it did address the issue with scaling of the particle shift. So now I'll switch to a little more practical experience aspect of getting this ready for Aurora. So there are two things at play here. One is the software, the other is the hardware. The software we are working with, as Chris outlined, is what we call the SDK, and this has been a sequence of alpha, pre-beta, and beta versions of Intel One API, to sum it up in the simplest way. This also is coupled with completely new compiler implementations on the part of Intel, with LLVM as the basis for them, but with new front ends as well. So XGC, when we started this, was all Fortran, and or mostly at that point, and we, identified quite a number of compiler bugs with the new IFX compiler, and worked with Intel to get those fixed, so that at this point it compiles all of the Fortran that remains in XGC, and in fact compiles the older, more Fortran heavy versions as well. Something that's hasn't been given a lot of attention is that, one component of this chain is the IGC compiler. So this is what I would consider the backmost end of the compilation path from an applications developer perspective, that generates the assembly that for the offloaded kernels to the GPU. So we've been working with a stream of versions of that as well for the working towards the Aurora hardware implementation. And there again, we've identified a number of correctness bugs and some performance bugs, the fixing of which has made a big difference for XGC. We've been using the testbed hardware that Chris outlined. I won't go say too much more about that, except that we started out like everyone else on the Intel Xeons with the Gen 9 integrated graphics, and since then I've been working on the other platforms. So it's really been the last 3/4 of a year or so that things kind of got over the fence and started ramping up with success for XGC. Q3 of last year we were able to run some standalone kernel tests of the particle push and the collisions and etc. on the Iris integrated GPUs. The following quarter, we were able to get all of those kernel tests to pass correctly running on the Articus nodes, and had some successes with running the full electrostatic XGC application. Since then, those issues have been sorted out, and much more recently, we've been able to run it on successfully the full application on the one of the Florentia nodes at JLSC with early access to that. One thing we did in the course of this was define a single node, really a single GPU benchmark figure of merit for tracking performance. This looks a lot like what one conventionally uses in a PIC code, except it's kind of reciprocal, so that higher is better, because that's what the Argonne Applications Working Group, which does quarterly surveys of applications that are targeting Aurora through ECP and ESP. They've asked for these applications to define and start tracking that performance metric. So the kinds of information they gather include that, as well as development status and functionality with the software kit. So as I mentioned, XGC relies heavily on Cocos. So we've been using versions of Cocos, some of which Yazi talked about in her talk. Our earlier focus was on the OpenMP target execution space, or backend of Cocos, which was the first one that was fully functional and we were able to get XGC to run with. More recently, we've focused more on the SYCL backend. So this is developed by Daniel Arndt, and we've had increasingly good success with that, and we've been able to run the full application with that backend. Just to return a little bit to this IGC component that I talked about before, you may have heard some discussion of just in time and ahead of time. So this is the IGC compilation is what does that. If you use JIT, when you compile your application, it has no GPU hardware specific information in the binary, and when you run it, it does a runtime compilation and subsequent offloading of the GPU kernels. Ahead of time is what will be used more in production and has more recently become functional with the software kit. And this at compile time, specifically when you link your application, it invokes IGC and builds into it, architecture specific GPU code into the binary, so then you don't have to wait for that to happen when you run it. I'll put in a plug here for the Friday tutorial that Chris mentioned. One part of this will be a breakout on Cocos for Aurora developers. And Daniel Arndt and I will head that up, and he'll give an update on the SYCL implementation. We'll give some examples people can try out, but we're hoping that people with Cocos applications will come to this with their applications. We can help them with getting started or trying things out, or with Q&A. We also hope we will be able to present some preliminary performance information on our PVC results in that session Friday. Thank you for support from the ESP project program, as well as ECP, through which I and Aaron get some funding through applications integration under HI, and as well as to acknowledge the widely distributed and large Cocos team. CS there in the red tie, he's the PI for the Early Science Project and co-PI for the WDMAP project. So thank you, and I'll be happy to take questions.
Thanks, Tim. Are there any questions? Yeah, I will say, with those of us that have been dealing with applications that make use of a portability layer, it's really been an interesting experience when everything is being developed, the hardware, the low-level software, the runtime, the programming model, the abstraction layer, the application itself. Communication is really important.
Is this you, Tim, on the left in the picture?
No, that's Robert Hager on the left, and Sang-Hui Ku and Stefan Etier on the right.
All right. If no questions, we'll go ahead and move on to the last of the 4 talks. In Yelo, will talk to us on his experience with the QMC pack curve, and in particular combining a couple of programming models. Slides look good, but I think you're still muted, Ye.
Can you hear me now?
Okay, yes.
Okay. I'm Yelo from Argonne. So today I will talk about the QMC pack early experience for preparing for Aurora. So my focus will be talking about combining OpenMP offload and SYCL. So the work is also with the help from Thomas Applicant from ALCF. So usual acknowledgement, just ECP support, thanks, and also all the hardware, software from JLC. So QMC Pack is a simulation app for materials, so solving the problem at quantum mechanics level. So won't go to the details. So give you a brief concept about the computer science aspect of the code. We are all, sorry, actually I forgot to turn on my camera. So we are using C++, most of the code, and also at higher level, at the course level, it's OpenPI plus OpenP threading. So think about that. All the CPU cores will be used by the threads, and all the threads will talk to the GPU. When it talks to the GPU, the programming model we choose is OpenP offload plus the vendor-specific programming model. The reason we need a bit of the vendor-specific programming model is we'd like to call the vendor-accelerated libraries. So, for example, when you are doing a certain calculation between 2 linear algebra calls, you need to deal with a bit of things. So we kind of smooth them out with the vendor native programming model and making sure it can asynchronous kernels can be stuck into those linear algebra calls. between them, make them fully asynchronous. So that's why OpenMP offload is our focus. Then vendor party is also our focus. So the benefit of using OpenMP offload is we just completely write a single source code. And so far it works well on the many vendor platforms, vendor GPUs. So for others, we have quite many choices for NVIDIA already. And AMD also have offerings from their ROCm or their AOMP research compilers when it comes to the Intel. So we use one API compiler. So Intel is also LLVM based. So generally we are quite familiar with its behavior. So most of the compiler study is done on the mini QMC, which is a mini app of QMC pack. And through mini QMC, you can see actually the 2021 0.2 release from Intel 1 API has already passed all the functionality check for mini QMC. And indeed, the latest compiler, one API compiler, can compile the full QMC pack and all the deterministic test, 99% pass. There's one failure, but this failure is likely due to certain numerical tolerance in QMC pack. So overall, that on the OpenMP side, the compiler quality really reached to a stage that can be reliably used. The compiler can be reliably used for doing actually code development or even getting close to test performance. So I did have performance data, but I cannot show you. Just a brief note that we constantly monitor this check SPO batch to kernel in mini QMC. So we keep record the performance of it on hardwares like V100, A100, and articles. So just keep benchmark. We collect the data over 2 or 3 years actually. For Intel specifically from the 2022 drop. So it's roughly started last October. The kernel performance becomes competitive to the market leader. Yeah. So this really a good news. That means for QMC pack needs, kind of all the pieces from Intel, the software starts to become in good shape. So since I mentioned, I'm going to talk about the OpenMP and SQL. So we have to talk about interoperability. So to achieve that, thanks to Abhishek earlier, he introduced the concept of context. So again, because we want to kind of do the linear algebra with SQL MKL library, we also want to use OpenMP to fill the data into these matrices we're going to operate. So somehow both programming model need to touch the same piece of memory that requires to have the same context underneath. So unlike CUDA, which has primary context per device, it's kind of implicit. SQL right now requires you to explicitly manage your context. So what we do is we make a query to the OpenMP for each OpenMP device. We extract the information about platform, the context handle, the device handle. We get it at a lower level, which is the level 0 level. Then we reconstruct it back into a SQL platform, device, and context. With those, actually later for SQL, we can construct queues. But that guarantees we are using the same context as the OpenMP part, so we can use the same pointer in both programming models. Yeah, so that's the way we handle the interop. The other thing is, by doing this, we kind of have the device control. So device control is mainly because context is from the OpenMP, so the device control logic is also kind of mastered by OpenMP. So we only need to control the OpenMP side of device affinity, device allocation to different MPR ranks. Then we receive it on the SQL side out of the box. Yeah. So since we heavily use OpenMP, we also know that from other GPUs like NVIDIA or AMD GPUs, that for OpenMP to have fast transfers, underlying it relies on the vendor APIs. In the vendor API, like CUDA driver API or HSA, it actually you get benefits from pinged host memory. SQL is the same. We use underlying its level 0, and also you get kind of you squeeze out all the performance from pinged memory. So what we do is using SQL. There are 2 ways actually to do it. In QMC Pack, it's C++, so we manage the memory allocators. So we can use the SQL API to allocate pinged aligned host memory. You can actually control alignment explicitly in the SQL API to get a pointer for the host, then later do map to the OpenMP. The second method is Intel OpenMP runtime library. I think offers you this OpenMP extension function. You can allocate host pinged memory as well, just through calling OpenMP runtime APIs. I think it will be eventually OpenMP specification, or just right now it's packed as an extension. So once you have those ping memory, just remember ping memory actually, every ping memory request requires interacting with the OS. So ping it, unping it is very expensive. So you should take advantage of OpenMP target data construct to reduce the amount of allocation, the allocation. So those optimization tricks, you can actually watch the video I put in SC20 for OpenMP. So the other topic is about how to do the CMake integration. So a lot of codes now use CMake. So CMake gives you great flexibility. So I think we can make best use of it, particularly for SQL. So unlike CUDA or HIP, is a CMake language. Actually, requires CMake extensive CMake support. CMake, so it depends on the version. You need the minimum version to support CMake. SQL is treated as a library. And it directly uses your C++ host compiler. So on the other hand, so the requirement is SQL kernels, when you compile them, they are lambda functions, and they are usually templates. So you need to compile them with the -f SQL flag option to activate the device compilation. On the other hand, SQL also has the host runtime library portion. They're just normal libraries. You only need to control the include path, linking path, and also the library file as well. So it can be very simple. So by separating these 2 notions, most of the code in QMC Pack, we can achieve to isolate the kernels into just a few files, which requires device compilation, so kernel compilation. While most of the header files, we don't include any SQL lambda functions. We only have template APIs, but without the definition. So by doing that, the majority of host QMC Pack code, like physics-related code, when it calls the SQL function, it's just a pure host call. So this also, this nice separation makes the compilation also fast, and you don't get into the troubles of slow compilation of template functions. One more thing to be noted is that at the linking stage, Intel compiler requires -f SQL option to activate additional device code handling. So when you do CMake, be sure to take care of that. If you don't do that, you will still link. If you just link all the object file or link the library together, you will succeed in linking, but at runtime, you may find kernel name found type of error, indicating that the device code was not added to the final executable. Just be careful of that. So SQL, since it's a library, it can be well incorporated in existing with the existing CMake feature. It doesn't require a specific language feature support in CMake. But in addition, you may want to distinguish Intel LVM compiler and the Intel Classic compiler. So that the only part that requires you to use 3.20 CMake version to identify this special LVM compiler ID. So this is the CMake portion. So the last thing I want to mention is about some notable difference between SQL and CUDA. So the execution dispatch has a bit of difference. So at the beginning, I was so used to CUDA queues, which is an in order queue, but SQL queue by default is out of order. So how to handle the dependencies in CUDA? You don't need to use events because in the order queue will ensure things are handled in one after another. Well, with out of order queue, you have to explicitly impose the events dependencies. However, I think there are also benefits from events because you can kind of enqueue things concurrently. Unlike the FIFO queue that it must execute in order. However, it just needs more developer attention to put the right dependency into the queue. But SQL does support in the order queue. I'm not fully familiar with what's the actual performance difference. I think it's something down the road we need to look at as we have more data experience and data with the SQL on the real GPUs. So right now the choice is heavily depends on the application. So at the API level, as I said, CUDA, you only see the CUDA stream becomes both the execution context as well as the synchronization mechanism. So you're passing the CUDA stream. While with SQL, you have to provide a queue as well as for the events. So events, you have the dependency events as in, and you return an event as out. So that's the notable difference when you program CUDA as SQL. What is next for QMCPAC? I think right now we saw that the code is for QMCPAC is running, but we are more looking at the performance, both the SQL portion and the OpenP portion. They're both built on top of level 0. Level 0 is moving very fast. It noticed certain things need to be adjusted, new APIs being introduced to maximize performance. Then it comes back to SQL and OpenP layer to make use of those features. So we would like to follow at least in the following months to work with Intel to reduce all the barriers and device synchronizations in their SQL and OpenP runtime implementation. Try to minimize those portions, those overheads, and overall it boosts the performance of QMCPAC. For us, of course, there is also coming new hardware, and for QMCPAC, we will keep an eye on it and make sure the performance match the spec or match our expectation. So that's it.
All right. Thanks, Jay. Are there any questions?
If I have a little time, I can do a clarification of out of order queue and CUDA.
We have time, but
Okay.
oh yeah, you can go ahead.
Yeah, so as Ye says, the advantage of out of order is like you may have more concurrency, right? Because you just say the only dependency will have the dependencies that you specifically specify. So the runtime may be running both kernel at the same time or overlapping data transfer and stuff. So this is the advantage of dependencies. right now, if you use a CUDA backend of OneMKL, out of RQ are implementing using one CUDA stream. So in fact, with a CUDA backend, out of order queue are in order queue, they are the same. But it is just implementation limitation right now. Work are ongoing to be able to implement correctly out of order queue. So one SQL out of order queue will be mapped to multiple CUDA stream, and they will dispatch kernel in those multiple CUDA stream. So this is the long and boring detail.
Yeah, my experience in general about this out of order in order. On the other hand, you can think about the OpenMP host tasking. It's a very similar situation. How to orchestrate all the tasks on the thread slots. Yeah, you can do it in order, you can do it out of order, and it's really a lot depends on the application pattern.
Yeah, 100% agree.
Any other questions or comments? All right, thanks, Yi. So I will close out the session with a few more slides. The folks can bear with me. So I just want, it's been mentioned a couple of times in the talks that we're, as part of our Aurora hands-on session, we're going to have the morning on this Friday dedicated to working with folks on the JLSC testbed. There'll be some initial discussion in the main room, and then we'll have a set of breakout rooms for more targeted discussion. And with this being NDA, we could have more open discussion of performance and issues that folks may be encountering, and possible resolutions. For those with JLSC access to the testbeds, you're probably accustomed that we keep all of our training documentation on the Confluence space. If you happen to miss the 1 hour session yesterday, we do have that the slides for that on the Confluence page now. And if folks are not aware of what Articus and Florencia nodes are, or they don't yet have access to the JLSC testbed and you're interested in doing so, we have information on the ECP Confluence page. And so if you go into the ECP Confluence and you type Articus or Florencia or Aurora Early Access, you should quickly find the page, and then it has the information to get access. And of course, if there's any questions, you can reach out to me. I'm happy to help. A quick plug for training events, that there are a host of training events, both on the public side and on the NDA side. And so there's a wealth of information that's out there, even more so than a couple of years ago, especially in the public space. So one event that's coming up in the very near future, I mean, already a month and a half away now, is going to be the next Aurora workshop. We don't have registration for that open yet, but we do have a placeholder page in place. And so announcement will go out to the broader ECP community soon for that. And so again, I would encourage, if you have an interest in participating in these events and getting onto the testbeds, I would encourage you to start the process for getting an account access. The sooner the better. And then lastly, a lot of the work that's been going on has been discussed as part of an applications working group effort. I think it was Tim that mentioned it. And so this has been a bi-weekly meeting that's been going on for the past few years, where Argonne and Intel participants get into the room. Now it's a virtual room, and really talk about progress on the software, the hardware, the applications, issues, both functional and performance, and really help everyone to move forward as we're ready for Aurora. In March of this year, now a couple of months ago, we started opening up the meeting to the broader community. We're doing it in stages so we can manage it. But really, we're interested in getting more of the developer community involved in the conversation, so we can start helping more and more folks out. And a key trigger for this has been the availability of PVC in JLSC. And so as we make that available to more users, particularly here with the ECP crowd in the next week or so, we were going to invite everyone that has access to the testbed hardware to join this working group discussion if you're so inclined. And so just as I had encouraged folks who have access to the testbed to go ahead and get access to the testbed, and to stay tuned for an invite on the ECP Aurora SDK mailing list for an invite to this working group. And again, there's a list, a link here for how to get access to the JLSC resources. And so there's a public link on the JLSC webpage if you look for how to get access, or you can look through the ECP Confluence to look for access. And again, you can reach out to me if you have any questions on that. And so with that, that concludes all of the planned content that we had for this early experiences discussion. And again, and unfortunately, we wanted this to be a public event so we could openly discuss things, and so that precluded a lot of discussion of performance and functionality in many cases. But I think I would want to encourage everyone to get access to the testbed and participate in these other events, and we can have much more open conversations and help you get ready for Aurora. So with that, if there are any final questions or comments, we can hang around and chat for a bit. Otherwise, I will end the session.
I just want to make one comment about Friday's session, that if you're interested and you already do have access to our JLSC testbed, make sure to join in the session a little bit earlier, because we have to go through people and make sure they are a part of the correct list. So in order to not lose any content, just join a little bit earlier so we can get you through. There will be a waiting list, so it will be different than this session. That's all I wanted to mention.
Thanks, Razi. So any questions, comments from the audience? Okay, I'm not seeing any takers. And so again, thanks everyone for joining today. Enjoy the rest of your Wednesday and have a good conference.
Thank
Bye-bye.
you.
Thank you.